the Eskay area, off to the area, west of the area we'll be exploring. This region has an array of mineral deposits in it. It's been studied for several years by Cliff Taylor of the USGS. He has a paper in press in the Society of Economic Geology. Will be coming out shortly, anytime now, in a special volume devoted to VMS deposits. And during his years of study, he looked particularly at the detailed lithostratigraphy at 11 different mining districts or mineralized districts in the whole of the Alexander Terrane, in the whole of the Alaskan Panhandle, from Windy Craggy, Mount Henry Clay, Greens Creek, and on down to Annette Island here. And this is the series of measured sections that, from industry work and his own mapping, measured sections and his interpretation of how they all fit together. On this distance is about 600 kilometers. We're talking about 250 kilometers long in the Eskay Rift. What he sees from the northern end at Windy Craggy moving south is that here you have a deep rift setting. He sees all of this as material preserved in a deep rift setting. The red is the sulfide accumulations. There's where Windy Craggy sits in the big scheme of things. The light gray color is siltstone. You see basalt units in green. You move down to Mount Henry Clay, and mineralization sits at a different horizon. The basalts are at a different horizon too. But overall, your assemblage is basalt and siltstone, not much different from what we see at Antioch. There's no rhyolite component here. You're in deep water setting. And again, at Greens Creek, some differences, but many similarities. But as you progress southward, some things change dramatically. Not only the mineralization changed, but the rocks change. You see less and less basalt. This green band here is the last basalt. It's thinner and eventually tapers out. You see a huge whack of rhyolite coming in. This yellow band, there's limestone units, but there's also coarse-grained clastic sediments, and finally a polymictic conglomerate. And the mineralization changes as well. You see less and less of the stratobound exhalative mineralization. You see something he shows, you have to read the whole paper, as little cross-hatched lines running across the stratigraphy. These are different stratigraphic horizons that have epithermal style mineralization in them. And the mineralization down in Annette Island and these other showings are all epithermal style, gold-silver mineralization at different stratigraphic intervals in this rift. It's shallow water to subaerial, and you progress over 600 kilometers from deep water exhalative VMS mineralization to shallow water subaerially exposed stratigraphy hosting epithermal mineralization. So it's mineralized from one end to the other, but the character of the geology changes and the character of the mineralization changes. The style of mineralization changes, all of its perspective. In addition to that, there's a major paper that was in preparation by Dick Silito and Jeff Hedenquist in a special volume, a bit obscure, but in a special volume funded by the SEG. While that was in press, Dick Silito produced a really short, January 2002, 3-page article, and he summarized the gist of what's in that major paper. The major paper is 30 pages of heavy-duty reading and head-scratching, and there's a lot of information, and it's wonderful stuff, but it's also heavy-going. This is a wonderful summary. It's like an illustrated abstract, extended abstract. Rifting, bimodal volcanism, and bonanza gold veins. He talks about this association. He's totally devoted to, focused on mineralization in rifts in subaerial settings. He's not talking about subaqueous settings now, but if you want to get started in reading about rifts in general, or this particular type of setting of mineralization, this is absolutely the best place to start. Now, 25, 30 years ago, life was a lot simpler for us. We only had one type of epithermal mineral deposit. Yep.
Can I interrupt for a minute? I'm run out of memory here, and this is really fantastic stuff.
Yeah.
I just want to get some more memory in there. Can you break for 2 minutes?
Oh, sure. Or I can take some questions.
Well, the questions are valuable as well. So
sure.
I think, okay. Well, take questions. No, that's great. Well, I just put some more memory in.
Go right ahead.
Thank you.
Think of 3 different styles of mineralization or types, and each of those styles representing a different geologic setting. Now, the bad news is that in typical rift structures, there's only one of these 6 subtypes of mineralization, of epithermal mineralization, that's preserved. The good news is that in a rift structure it's abundant, and it turns out to be the highest grade of all these different styles of epithermal vein mineralization. That is the bonanza veins, which by definition are greater than or equal to or greater than 1 ounce per ton gold. The other feature here sitting in the rifts is alkalic style epithermal vein systems, and these are characteristic of what they call abnormal rift structures. Now, the rift structures are normal rifts, but they're in abnormal, atypical rifts, not abnormal, atypical rifts. They're in unusual geologic settings. And the other place where you find alkalic style epithermal mineralization is in calderas, so a rather confined space. So both of these styles of mineralization are related to deep crustal faults, but this is the one that is characteristic of typical rifts. So if you could only pick one of these styles of mineralization that would be characteristic of a rift setting, this is the one you'd want to pick, and that's the one that sits there. The other thing that showed up in the paper that Silicon Hedquist published in 2003 is this interpreted section, schematic section to a rift. This is a subaerial setting. They're talking about totally subaerial settings and epithermal style mineralization. This is the floor of the rift, the pre-rift rocks. This entire white or gray section is the, however complex the volcanosedimentary sequence symbolized by just one color. What he was emphasizing in this diagram was the relationship between the rhyolite domes, which they see as the heat source that drove the hydrothermal convection system that formed the veins. Is even though these are the rocks that form the epithermal veins, you're going to see a really unusual pattern of distribution of epithermal veins. They could be in the immediate footwall to these rhyolite domes. Well, you might think that if these are the heat source, the veins would be forming somewhere up above them. But one of the things they realized in studying these things around the globe is that the veins can be in the immediate footwall. They can be some distance away because these big piles of rhyolite are generating huge hydrothermal convection cells. So you can actually be depositing veins some distance away from the rock that is the heat source. The other feature that is a key or clue to the fact that you should be looking for epithermal mineralization in the area is unmineralized sinter terraces. These are silica sinter terraces. They can be laterally, because they're going to accumulate where there's a depression on the haliosurface, laterally some distance away from the rhyolite dome itself. They can be laterally some distance offset from the veins that are in somewhere down in the footwall. And the other point they emphasize is that even though it might appear geometrically that the veins and even these cinder terraces might be related to basalt flows, that genetically, in terms of their studies, whenever they've been able to narrow these things down, it's the rhyolite rocks that are the heat source, not necessarily the metal source, but the heat source driving these convection cells. So you would have to explore a considerably larger area than just the immediate vicinity of these rhyolite structures there. So that was the point they're stressing with this interpretive diagram. I want to come back to the Eskay Rift and talk about the things we've learned from these other studies and emphasize some characteristics to show you that there are different things to be learned by studies in different segments, these preserved segments. We'll start at the south, the Georgia River Pendant here, and we'll work our way north through Eskay Creek Mine area. There's quite a detailed story to say there. I'm afraid it'll take a little while. Sedimentary unit, middle sedimentary, up to Table Mountain as well. So we started at the Georgia River Pendant, which is a large block of Triassic and Jurassic volcanics and sediments preserved, completely surrounded by Eocene age intrusions north of Antioch, west of the area you'll be working in, your BMS claims. At the southern edge of this, as the results of Carol Evanchik's mapping, there's a band of basalt, siltstone, and rhyolite. No surprise. That's preserved through here. There's now good geochron constraints on it. These are Eskay age rocks. You're looking at about a 12-kilometer strike length. There's about 8 kilometers of exposed strike length of rhyolite. These are weakly pyritic, but the enclosing siltstones are more strongly pyritic. These have been about 5 kilometers in thickness. There's been exploration in this area over a series of years by a company called Praxis. Most of that exploration was concentrated on drilling porphyry-style mineralization around the perimeter of this stock, this early Jurassic stock. There's very little exploration, virtually none, anywhere in this belt of rocks, because at the time they were doing their exploration, they didn't appreciate the age and the significance of this rock package. So that from the coast, most of this is forested and steep terrain, but there's a Mount Carr here, and it's superbly exposed. It's one of the strongest iron oxide thematic mapper anomalies anywhere in this entire region, is the pyritic siltstones on top of Mount Carr. Flow-banded rhyolite flows, and an area that has very little exploration attention to date. You come up into the area of the Eskay mine. A couple of things. These red bands represent there's the Eskay mine. This is the little piece of basalt that was on Bob Anderson's original map because he only showed the basalt, shreds of erosional remnants of basalt. This is the next piece further south at Mount Madge. But in actuality, if you include the rhyolitic rocks and some siltstones and a little bit of other clastic rocks, this is a continuous belt of Eskay rift stratigraphy that's exposed and preserved through here. These are still the interpreted boundaries of the rift, or the newly interpreted boundaries. We've snugged it up and brought it in really close. It's about 7 kilometers east to west across here. Talking to Carl Edmonds, who was in charge of exploration at Eskay mine for many, many years with Homestay, he said they sent out at 4 different periods in the life of the mine. They sent geological parties out into the they mapped the whole region, they explored it all, but they sent them off to the east of the mine, just 300 or 400 meters off the east of the mine, to follow the rhyolite eastward, down off the cliffs, down into the Unit River Valley. There's the Unit River. It's quite extreme terrain and lots of vegetation and talus and stuff, but whatever they find outcrops, follow those rhyolites, because that's the key. That's what sits in the most of the mineralization associated with the rhyolites at Eskay mine. The first crew that went out in the first summer didn't get very far before they ran out of rhyolite. Found dacite, and then there was a big debate about whether dacite's really rhyolites or whether they're different. But there is dacite in succession, and they're distinctively different rocks. So somehow they missed the rhyolites because they'd only gone 300 meters from 400 meters to the mine, and they haven't found them again. They sent another crew out a couple of years later with the same sort of impetus and emphasis to follow these rhyolitic units, and they came back stumped as well, although they added a lot more detail to the map. They've done this at 4 different phases. They've sent geologists out chasing the rhyolites down over the cliffs in the Unit Valley. They weren't happy geologists because it's nasty terrain. Or dropping them off at the river level and having them map back up to home and dinner, which at least gives you a little more incentive to take it back. In any case, after 4 episodes of this, they finally realized something that we'd interpreted as well in our maps. I only had this conversation with Carl after I presented this around it. He came up and talked to me about it. When I said that we moved the boundary, even when we're just interpreting the boundaries, the bounding faults that we brought them in close to the last exposed outcrop. After 4 episodes of this chasing the rhyolites, they realized that the reason they couldn't find any more rhyolites after they go 400 meters east of the mine is that's where the rhyolites must stop. That has to be where the edge of the rift is, at the Eskay mine area. They have no constraints over here to the west, 7 kilometers this way, or about 9 kilometers this distance, except that we've known for years that the favorable geology of the rhyolite, the basalt stop here, the rhyolites and the sediments that look like rift-filled rocks stop abruptly here, and everyone's thought, well, there must be a young fault that cuts them off. And the only thing I changed now is, well, they're definitely cut off because you can't find them when you go any further west or southwest. But maybe it's not a young fault, it's probably the bounding fault of this rift structure. So what you're really seeing in this interval of about 9 kilometer strike length along the crest of the Eskay anticline here is you're looking at the entire width of the Eskay rift exposed in outcrop in this area. And that's probably the only place we can do that with any certainty. So here's the different styles of mineralization. At the Eskay mine, there is, in the footwall rhyolite, the stockwork feeder zones that are quite extensive. Also the 109 vein, which is an epithermal style vein in the footwall. With passing geological time, as you go up in the section, you get strata-bound clastic sulfides that are remobilized, reworked, deposited in the mudstone. This is the main ore body of B zone in Eskay Creek. And then the hanging wall zone, which is a more like a Cypress type, deep water, copper pyrite rich VMS unit within the basaltic units in the hanging wall. So this suggests that your depositional environment is actually getting deeper as time passes. And then here's the footwall sequence, which is right near the top of the Hazelton's regional Hazelton stratigraphy. That's the interpreted base of the rift. I think those are the points I want to make here. Oh, and then we move on to a model, a much more sophisticated, complex model than the one we looked at. This is a laboratory model of a rift structure. Turns out that a lot of the recent research is going on to the formation of rifts, the mechanics of rift formation is being funded by the petroleum industry. Who knew? They're keen on this because the sediments that accumulate in a rift structure tend to be reduced sediments. There's not a lot of oxygen down there, so you get highly organic material. So there's great source rocks for oil. And on top of that, you get all these wonderful structures and many, many small structures that are are their optimum traps for oil. So drilling in a rift setting, paleo rift setting, exploring for oil, you wouldn't expect to find the gigantic, extensive oil fields that are localized along anticlinal domes as there are in the Arabian oil fields, but you can find many, many small oil fields all in a small area. So you have an oil field rather than a field of oil sources rather than one big oil deposit. So that's what's spurred this funding. So this particular model, this is a photograph from above. It's in a laboratory. They lay this down. This looks like a really horrid candy my wife likes, called licorice all sorts. This is all fine sand. These are layers. It doesn't take them ages just to build a model. Colored layers, alternately colored layers of fine sand, blue, white, black. These colors are the pre-rift stratigraphy. Then to make this work, there's a metal plate here that lies under the model here, another one here at an angle. This particular exercise are studying oblique rifts, rifts that are extending at an oblique angle to the direction of the actual fracture. And then under this interval, there's a rubber sheet. So they crank the model a little bit on a couple of nuts or whatever they use of screws to make this move a little bit, and as it settles, they put in the rift fill stratigraphy, which is these orange, cinnamon, and white units. And then they turn the screws a little bit further and add a little bit more sedimentation or rift fill stratigraphy, whatever that happens to be. Again, fine sand, different colors. And they just keep evolving this thing and letting it grow and recording it, photographing it as it fills up. And they get this diagram here. It's hard to look at. The lighting is from the right, so the black lines you see here are east-facing scarps, and the light-colored lines you see in this are west-facing scarps. They try to represent it schematically. Again, the black lines are east-facing scarps. The red or cinnamon-colored lines here are east-facing scarps. Same as the diagrammatic version of this photograph. But you can see the other thing that's interesting is the fracturing, the faulting, the scarps within the rift. There's the bounding faults. There's bounding faults here. But the scarps end up reorienting themselves so that they're perpendicular to the direction of extension. That's part of their story here, why they're doing this study. I want you to look in particular, the point I want to make relates to sections 5 and 6, which are here in these photographs at the bottom. We talked before about how the floor of these rifts founder asymmetrically. They drop down and one side will be tilted. It doesn't drop down nice, stay nice and horizontal. The reason this is significant is you also know that in the Eskay rift, parts of it are subaerial, parts are deep water ocean floor, and then some point along that 200 kilometer length, there's got to be a point that's somewhere right near the paleo surface. At some point, the seawater that's filling the rift actually stops and becomes subaerial. You saw that photograph from Africa where there's that arm of seawater comes in. That has to happen here too. We know that in a totally subaerial environment, exposed to the atmosphere, the hydrothermal mineralization concentrated in this rift will be epithermal in style. In a totally deep water subaqueous environment, it will be exhalative in style, it'll be VMS style mineralization. But at some point when you get near that transition, you can appreciate we have to have a situation, because this floor is uneven, it's tilted, founders asymmetrically. You could have a situation where the water depth was just right, so that at one point, not across the length, but across the width of this rift, you could have subaqueous hydrothermal activity, where at the other side of the rift, just kilometers away, you could have, if that's the water depth, subaerial mineralization happening in the same place. In the cross section, you don't have to go hundreds of kilometers on length. And the reason that I think that is significant, this is in much more detail. This is on an inset from one of the maps. There are 30-odd, 40 mineral occurrences along this band of the rhyolite. In this case is kind of a limey green color. The basalt is this green unit here. This is the only piece of the basalt of the rift field sequence that's preserved. What I want you to appreciate is these are all the mineral occurrences there. Most of the ore bodies of the Eskay mine are right in this area. There's lots of mineralization both in the basalt and because it's projected up through the surface in the immediately underlying rhyolite. All the mineralization is in the rift fill rocks, the rhyolites and basalts, and this contact mudstone, which is so thin, 30, 40 meters thick, it doesn't even show up on this map, which was created at 1/50,000 scale. But as you move south, and you've only got 9 kilometers down in here, 9 kilometers south in this area, the mineralization, there's lots of mineral occurrences there, sits down in the footwall stratigraphy. The pre-rift rocks are down in the footwall, in the conglomerates and the dacites. And these are cross-cutting veins and vein networks, vein systems. They're precious metal rich, they're pyritic, lots of alteration around them, but they're all down in the lower stratigraphy. And the tendency if you've gone to sample them to see if they're precious metal rich, and they're elevated, but they're not economic in their own right, and then to turn west and go up strata and look for the strata-bound, the desired strata-bound exhalative mineralization that's characteristic of the Eskay mine deposits. In which case they do that and they don't find anything, in part because the pillow basalts are eroded away, but the rhyolites are there, and they just don't find that kind of strata-bound mineralization or even alteration associated with it. And what I'd suggest now that we know more about the mechanics of rifts and the morphology of rifts is that in this area maybe the mineralization we're looking at is not subaqueous exhalative style mineralization. Maybe these veins are in place and these are actually subaerially exposed, or in a subaerial environment, deposits of epithermal style mineralization. And if that's the case, what you should be doing is looking at the veins themselves as the sweet spot, as the best it's going to get, or look down section or along strike, but don't concentrate all your exploration efforts from these mineralized veins up section. Look at the veins themselves, because you may be in an epithermal environment. We know for certain that at least part of the time the mineralization was ongoing at Eskay Creek. It was shallow water during the time of formation of the 109 mill. So this could still be shallow water environment, because know that the floors of these rifts can be tilted even over short distances. There's another lesson to be learned from what we found in the mapping at the Pillow Basalt Ridge area. This is all rift fill sequence, a vast mountain of, a ridge, but really a mountain of pillow basalts. This is a schematic section. This is a cross section, get that in a minute. There's a lower basalt sequence, at least 2 kilometers thick. We know it's at least 2 kilometers thick. It's a 2 kilometer deep drill hole that was collared in it and drilled down 2 kilometers and was still in pillow basalt. The hope was to drill through the pillow basalts and hit a rhyolite horizon or mudstone horizon like at Eskay Creek, but that never happened. There's a small, it's exaggerated thickness here, about 30-40 meter thick mudstone, siltstone unit with rhyolite shown in yellow, and the basalt units as well, thin basalt flows that aren't shown in the schematic diagram. And then an upper basalt sequence that is, again, is at least a kilometer thickness, probably greater, and an upper siltstone unit, which is this light gray band. It's not part of the story, but that's where it sits. We're looking at least 3 kilometers of stratigraphy exposed in pillow basalt ridge, most of which is pillow basalts with this intermediate middle siltstone, rhyolite basalt unit. Here's a composite cross section, north to south here, showing the north limb, dipping northward, and the south limb. This is where the drill hole was collared, right here in the siltstones, drilling down to depth. But there's a difference in geology between the rocks exposed to the north and here. The only rocks in this middle sedimentary interval are pyritic siltstones. They're weak-lead pyritic, they're gossinous, no particular metal values, but that's where they sit. By the time you get to the northern limb of the anticline, you have rhyolite flows and local small rhyolite domes, the basalt layers, which aren't shown here, and the siltstone. These are also weakly pyritic, and again with no particularly appreciable values, but the impression you get from these two contrasting geologic sections is that this is more proximal to the volcanic center, because you got little rhyolite domes. And when you reach this part of the clay block, the Homestay Barracks clay block, there's a major thrust fault that cuts off all the rift fill sequence at that point, which is the end of the story. Or is it? That's what was thought. The ground that continues to the north is this block in here, and it hadn't been mapped. It had been prospected during the early frenzy of exploration. It had been prospected, but never been mapped. The companies hadn't mapped it. We hadn't mapped it. We got in there in the season after doing this work. We got in there and mapped this block of ground, and what we found was the lower basalt sequence, the upper basalt sequence, exactly as we'd shown. There's a fault here that throws this stratigraphy back up into place and preserves it. So even though it's cut off by this thrust fault, a second fault brings them back into play. And the mudstone, the intermediate mudstone, middle mudstone rhyolite unit that was already mapped and recognized here, shows up in this area as a massive rhyolitic unit composed of multiple rhyolite flows and intense concentration of rhyolite feeder dikes, about 10% pyritic siltstone in between the rhyolite flows, and no basalt whatsoever. So in terms of proximal versus distal, this is very distal because there's no volcanic component in these mudstones. These are fairly minor. You're probably looking at 40% rhyolite, 40% basalt, about 20% siltstone in this interval. And here you're looking at 90% rhyolite and 10% siltstone in this interval. And no one was aware of this. So that what you look, when you stand back and look at the bigger picture, including geological information from two adjacent claim blocks held by competing companies, this looks like even more proximal and therefore more prospective ground than this stuff to the south, which has that very expensive drill hole invested in it. So the more you can see, the more you learn. We move north to Table Mountain, which is west of Barrage Airstrip, east of Shaft Creek Porphyry, south of the G.J. Kiniscan, north of the Hank epithermal deposit. It's about 8 kilometers wide, it's about 22 kilometers long. It's not a perfect plateau, but it's fairly level and is totally exposed up above the alpine, so it's just rock and gravel and talus and moraine. In this section, this line here between the palest green and these other green and brown shades is the line, the western bounding fault of the rift. And this is the point where Joanne Nelson mapped that right about here, that first place we found one of these constraining faults of the rift structure striking northwest. There's a lower basalt sequence, the colors aren't a perfect match, but a lower basalt sequence, a middle sedimentary unit, not that dissimilar from Basalt Ridge, but the dimensions are dramatically different because each of these is about 1 kilometer thick. And then an upper basalt sequence, total stratigraphic interval about 4 kilometers. Two styles of mineralization associated. Oh, the other thing I want to emphasize before I go too far, even though I show this schematically as a thick unit, about 1 kilometer thick, at its southern end it pinches out completely. At its northern end it's over 1 kilometer thick, this middle sedimentary unit. So you could walk this section here and see nothing but basalts and not know you changed through different basaltic units. You walk the section here, you go through over 1 kilometer and a half of siltstones, and you might think you're in a totally different geological environment, not realize you're looking at this evolution over about 10, 12 kilometers of strike length. Two styles of mineralization. One is sulfides concentrated right at the contact, at the base of the middle sedimentary unit, or at the top of the upper basalt unit. There's an incredibly long zone of exhaled mineralization, footwall stockwork, and the basalt, and right at the base where you get into the first fine-grained clastic sediments, exhalative pyrite, with really no significant base metal values except in 3 locations at Grizz, Compass, up here at Zinc Moss, which is a different stratigraphic interval but similar geologic setting, basalt and an overlying clastic sedimentary unit. These have elevated lead, zinc, silver values in them. At these 3, this is Arnie Berkland discovered this a couple seasons ago, prospecting. In addition to that, around these rhyolite felsic domes, these are thought to be cryptodomes, so they're not domes exposed on the paleosurface. They were rhyolite bodies that extruded up along dikes, feeder dikes, into wet sediments, and the sediments were wet enough that the rhyolite stopped there and chilled out and formed a dome completely surrounded by sediments. So you get all this breccia, talus breccia accumulating, debris accumulating around these domes here. And these are, the rhyolites themselves are pyritic, the clasts are pyritic, and the sediments, the immediately surrounding sediments are all pyritic, and that's what's represented by these little yellow dots in here. So that's the story at Table Mountain. There's both strata-bound, syngenetic, stratiform sulfides, as well as this mineralization, disseminated mineralization around these felsic domes. So, but they're very easy and they're barely explored. They were discovered for the first time in '91 by an Noranda exploration crew. They prospected in '91. They went back with regional geophysics, but not a lot of trenching and drilling, but regional geophysics over the whole plain block, because they liked the results from the prospect. '92 and '93, of course, was the Windy Craggy decision where Noranda announced their leaving BC altogether, so they walked away from whatever this would become, and it's only now getting looked at again. So I looked back at, I stood back and looked at what we knew about mineralization in these 2 parallel rift structures formed at 50 kilometers strike length, and tried to pick some areas where we should be particularly focusing our efforts. I didn't put a lot of imagination into this because the ones I ranked the highest, shown in red, are all areas where we already knew there was strata-bound, syngenetic, exhaled-style mineralization, table mountain at the Eskay mine area, in Mount Madge area, and down here at Antiochs. But then I put a second order here in yellow of two different categories of areas that deserve follow-up. These are areas that have either favorable geology and some sign of sulfide mineralization with them, which are many of these here, Luigido, Arctic Grid, and so on. And then a second category also included here that worthy of follow-up are these five. There's five in there because these two I've put together so small. 5 zones of erosional remnants of rift-filled stratigraphy that are known from mapping that was done in the 1960s. And these pillobasalt sequences were all discovered by mapping that was follow-up to the discovery of the Grand Duke mine. Grand Duke's hosted in pillobasalts, or Triassic pillobasalts, but the company went out and started looking particularly for pillobasalt sequences, found these and explored them, but they didn't know anything about the rift story in 1964, and these things haven't been looked at since. They're remote, they're small, and the reason they're on this map as prospective, as deserving follow-up, is because we know so little about them. Not because we know a lot about them, but there's so little, we really don't know whether they're significant or not. So they deserve another look. The other thing to emphasize for this is that we know that in this western rift, there is syngenetic exhaled mineralization at Eskay mine at the north, mineralization in Antiochs at the south, and past producing mines, stratabound syngenetic mineralization, stratiform mineralization, Table Mountain, and down here at Ilians Mountain and left over Yankee Boy as well. So from the northern end to the southern end of both these structures, there is exhaled mineralization preserved and already documented, as well as so there's no place along these rifts that should not be prospective for exhaled mineralization. And finally, one left lateral leap from South Africa. This is a schematic cross-section across the Witwatersrand Basin. This is an inland lake. It's a lacustrine basin. It's not marine. It's a freshwater basin. So it's like Lake Victoria in the center of Africa there, all rift-hosted basin. This is just one side of the diagram to show the schematics. And here you can see, again, in this paper that was published by Dick Hutchison in 1993, you already knew about these sequential bounding faults of the rift. Here's the earliest one. At some point it locks. So this becomes the next fault movement, earlier basin edge faults here. Here's the active one, the current one, the story, and you can bother to cartoon in the future developing basin edge fault as they evolve inward. You have Archean terrain, which is the country rock around this, and this basin is filled with, at the lowest level, the mixed volcanics and clastic sediments, basalt, andesite, dacite, and thick volcanic succession with intercalated sediments. And then the main coarse clastic sedimentary basin fill, the lake fill, which is the West Rank Group, the stuff that hosts the gold-bearing pyritic conglomerates with the Witwatersrand Basin. And then the last sedimentary interval preserved in the basin is a series of fine-grained sediments here, siltstones, ferruginous iron-rich shales, and I'm looking for you, there they are, algal beds, but very shallow water, muddy, quiescent type deposits after these high-energy coarse clastics accumulated. The model he had for forming the gold deposits in here was that you would have the metals are leached from these volcanic rocks. The metals that are already contained as part of the base level metal content of the volcanic rocks is leached out. The metal-bearing fluids are looking for any path of least resistance to get out of this high-pressure environment, and they travel laterally along the sedimentary beds until they find this bounding fault. And that, of course, is a major aquifer, or a route out to the surface to a lower pressure area. So they start heading upward at a high rate of speed. And in a normal setting, they would be forming exhaled mineralization on the paleo surface here, the lake floor, and forming quiescent exhaled style mineralization, depositing out those metals in sulfide lenses. However, there's another part of the story, and that is that this is a high escarpment here, and the high energy creeks and rivers rushing off this Archean terrain with cobbles and boulders of whatever mixed lithologies there are, but a lot of quartz, because you get a lot of quartz off the greenstone belts from the Archean terrain. they get ground up, and the last rock to survive out of all the lithologies will be that quartz, and you get a disproportionately high content of quartz pebbles in the gravels that are washing down in here. And this discharges off the cliffs, the scarps, into the lake basin, and churns up and disturbs and just redistributes the sulfides that wanted to accumulate in a quiescent environment, and distributes them within the gravel conglomeratic alluvial fans that form this West Rand group. And these are the pyritic gold-bearing pyritic conglomerates of the Bottom Trend Basin. This hydrothermal model is still being used in the latest literature. The only change they made in this is to say that they leave this part of the story out. Say these hydrothermal brines, metal-bearing hydrothermal brines for leaching metals from the Dominion group, come up these bounding faults, but when they reach certain horizons within permeable horizons within these the pebble conglomerate horizons, which is the most permeable, they move laterally in there, and the gold precipitate and the sulfides precipitate out along carbon algal mats, carbon debris, organic debris within the unit. So that the early part, the first part of the story is still being used in the interpretations, formations of these gold-bearing conglomerates. Why is this got anything to do with the Eskay Rift? Well, that's because there's just one area here on Table Mountain, this area here where we have this conglomerate. It's really a breccia because very few of the clasts are perfectly rounded. They're sub-rounded, some are angular, some are quite sharply angular, and that's this yellowy colored, murky yellow colored unit in here, quite widespread. It's got some bounding faults on it. And we already knew where we found fragmental rocks, debris, talus debris here, that this was a carapace or a fan around a local rhyolite dome, a rhyolite center. So we found this huge interval, and we're talking about hundreds of meters, of pyritic, rhyolitic class conglomerates, entirely made up of rhyolitic class, pyritic, just like this pyritic rhyolite apron, plastic apron sitting around these domes. We knew that this is such a huge accumulation, we had to be sitting next to the mother of all rhyolite. It's a really big slug of rhyolite in place, and we never found it. We walked up through this section, we walked this exposure about 2.5 kilometers along strike, hundreds of meters thickness. It was a bit of a puzzle to us of what this represented because it looked exactly like this rhyolite talus and debris here. We know more about these things now, and what we think we're looking at is, well, here it is. Up close, boulders of pyritic rhyolite, rounded, sub-rounded, angular class of pyritic rhyolite. The material in behind it, in between, is poorly cemented pyritic rhyolite sand, pyritic sand. It must be a carbonate cement because it weathers out so quickly. This is about 100 meters of cliff. You can see the coarse, crude bedding of these things. There's hundreds of meters more, both down section and above, and about 2 kilometers, 2.5 kilometers strike length. We took 3 samples from this only and assayed them, but those 3 samples didn't carry any values at all. Maybe that's all there is to the story. On the other hand, it's not difficult to go into the Waterfront Basin and collect 3 samples of pyritic conglomerate. They won't carry gold either. But the point we want to make is what we think we're looking at now, in hindsight, is that this is an accumulation of pyritic rhyolite talus along the, I'll back up one. Whoop, boy, that was exciting. Along, pyritic rhyolite talus along one of these bounding scarps. So there might have been, before I got eroded away, one of these perched rhyolite flows on the escarpment in the near rift facies, and it eroded. All its debris was cascading down with the actual bounding scarp of the, as we saw in those photographs from Africa. So you've got a big talus fan. This is subaqueously accumulated, so it's crudely bedded, coarsely bedded, but it's still really angular. So you've got this huge fan of pyritic. There's pyritic talus there, and this has not been adequately explored or investigated to see if there's any accumulation of gold or of any other metals anywhere within it. But I just want to make people aware that this geologic phenomenon exists within the Eskay Rift as well. It's not particular to the Waterfront Basin. So what have we learned about the Eskay Rift from hard work and previous studies? We've got a twin rift model that reveals both new target areas, and you double your exploration, your prospective strike length from about 250 kilometers to 450 kilometers. We know that it can vary from shallow water to deep water progression in the Western Rift, that progression moves from north to south. They're both VMS showings and VMS potential along the entire 450 kilometers in both of the rifts. There's VMS style mineralization, exhaler style mineralization. There's epithermal potential in shallow water subaerial sections that hasn't really been fully assessed. We know there's a potential for pyritic talus and conglomerate that's been untested. And many of these 25 segments, erosional remnants are fully explored. Prospecting is both essential and successful. The two most recent VMS showings, new VMS showings that were discovered are Arnie Berkland's discovery in Table Mountain 2 years back, and then the discovery of the Smitty Zone on Kenridge ground. Both of those were prospecting up creeks in outcrop, so it wasn't geochemistry, it wasn't so much geology or geophysical approaches and prospecting, and they knew what they were looking for, and they knew they were in the most favorable distribution. So that's the story.
Excellent. Okay.
Terrific, Danny. Really world-class science delivered in the storage shed. Thank you very much.
Yeah.
That closing emphasis on prospecting, I think, is really key, Greg. And one of the goals we could have, I think, for the next couple of days is, while you're here, to try and get together a few reference specimens for everyone to have a look at, so they know what they're looking for when they're wandering up and down the creeks. Really, really important.
Okay.
Please. Yeah.
Question? Now or later, anytime it comes up.
Where our claims are located, we're looking more in the deep water environment. From